Hello students, how are you all? So it is nice to once again come back to the subject. We are going to do the numericals today. So I'm starting with the numericals based on Newton's law of gravitation and Kepler's law. So it is given in page number 504. You can turn to the book. So the first part I'm not going to do, you can just read yourself. Question number 2 I'll do. A rocket is fired from the earth towards the sun. Now look at this one. You are firing a rocket from the earth towards the sun. It is going towards the sun. At what point on its path is the gravitational force on the rocket zero? That's what the question is. Now rest everything is all the constants. The values are given. Mass of the sun, mass of the earth, and then neglect the effect of other planets, etc. Orbital of the thing is given there. So it is just a one line question. Let us once again try to understand the question. So what you're doing is, so there is earth. You can draw this diagram, and there is sun. And this one, from here to here, you can say from this center to center, r is the distance. So this rocket is going straight. At one particular point of time, right, you'll find maybe somewhere here, you'll find the gravitation pull of on the rocket due to the earth, force of earth, because force is always pulling, the body is being pulled towards the earth. And there will be again in this point, there will be force of the rocket towards the sun also. Now wherever the rocket is going, here or here, every time there will be two forces will be acting. One is towards the earth, one is towards the sun. When it is close to the earth, which force will be greater? Earth force will be greater, because earth is much more closer to this one. And when it is going far away, earth force keeps on decreasing. And as it goes closer to the sun, the force of the on the body due to the sun will keep on increasing. The force will be increasing. The force due to sun will be increasing as you go ahead. And as you are going closer to the earth, the force due to earth will be increasing. So what happens is, so here when the rocket is going, so when rocket leaves earth, force on the rocket due to earth. The force on the rocket, as it keeps on going, force on the rocket due to the earth keeps decreasing. Is it not? So that's going to be decreasing. This force due to the earth, as it goes on, it keeps on decreasing. And force on rocket due to sun, what will happen? Due to the sun, the force keeps on increasing. So there will be a point where both the force will be equal. The force due to the force of gravitation due to earth keeps on decreasing, and the force due to sun keeps on increasing. That will be a position where both the force will be equal. So this point, if both the forces are equal, we consider as D, and the rest of this one is considered as R. So let O be the point where both gravitational force are equal. Force due to Earth is going to be equal to force due to S, Sun. So what is force due to Earth? Look at the gravitational formula. G me small m upon d square. The next one is G, mass of the Sun, and mass of this one upon r minus d the whole square. Let me explain this one. This is mass of the Earth. This is the mass of the Earth, right? And this is mass of the rocket. It is here. And what is the distance between the rocket and this one? D is the distance, d square. Now the same force of the mass of the rocket towards the Sun. So these two bodies has to be taken. Mass of the Sun, this is the mass of the Sun, ms, and then mass of this rocket, m, and the distance between them is r minus d. So you have to equating. Now what you need to do, go on to cancel these masses, right? These two are cancelled, g got cancelled. So what is the next part of it? So you can write ms upon me, keep here itself, is brought down, r minus d upon d the whole square. Why did I put whole square? R minus d, if it goes up, d square, so it is going to be whole square. In other words, r minus d upon d is equal to under root of this one. Now you can look at the parameters and find out what are the things it is given there. What are the things which is given there for the mass and for the radius and everything, right? So let us look at the question now again. The question says mass of the Sun is going to be equal to 2 into 10 to the power of 30. Now look at this one. Mass of the Sun is going to be 2 into 10 to the power of 30. Mass of the Earth is 6 into 10 to the power of 24. And mass of the radius of the orbit is going to be equal to 1.5 into 10 to the power of 11. Let us write these also here. So I'm just writing for you. Okay. So mass of the Sun. So mass of the Sun is going to be equal to 2 into 10 to the power of 30 kilograms. Mass of the Earth is going to be equal to 6 into 10 to the power of 24 kilograms. And R is going to be equal to 1.5 into 10 to the power of 8 kilometers. 1.5 into 10 to the power of 8 kilometers. Right? Now, you can substitute these two things. Mass of the Earth and Sun. Substitute here. So it is 2 into 10 to the power of 30 divided by 6 into 10 to the power of 24 is going to be equal to, you can make this one also as R upon D minus 1. So once you do this calculation, this will get cancelled out, it will become 1 by 3, and when you do this calculation, you will land up with an answer of 577 is going to be equal to R minus D minus 1. So what is R minus D? Minus 1, it can go here, it is 578. So we know already what is R, we have to find out D. So what is R? R is going to be equal to 1.5 into 10 to the power of 8 kilometers. And we need to find out D. So it's going to be equal to D, and this one can come down 578. You can easily find out this value. Finally D is going to be equal to 2.6 into 10 to the power of 5 kilometers. If you have a calculator, you can do it fast. This whole of the chapter needs calculator. Much heavy usage of calculator will be there. Okay. So we'll go to the next question now. Question number 3. Question number 3 is a very straight question. That talks about, just read the question. Look at a book. Take a book and take a look on it. How will you weigh the sun? Big question. How can you weigh the sun? You cannot have a physical balance. You cannot go near the sun itself. You can just keep watching it blazing so fiery. Now it is that let us estimate the mass. It's asked. How can you weigh it? How can you estimate the mass? There are two parameters given here. The mean orbital radius of Earth around it is 1.5 to the power of 10 to the power of 8. The radius is given there, and we already know the time also, the time period of revolution. It takes Earth to go around the sun for one full rotation is going to be how much time it takes? 24 hours? Or how much? It is 365 days. Now, let us do this numerical now. Okay, so R is given here 1.5 into 10 to the power of 8 kilometers. So you are going to weigh the sun. Sun, you need to weigh it, and Earth is a orbit. It is going around this orbit. This is Earth. So what you can do is you can try to compare these two things. Okay, now once you do the force on Earth due to sun, force Fs is going to be equal to G, mass of sun, mass of Earth, and the value of R, the whole square. This is the value of R. It's already given there. The next line is this force contributes to centripetal force. So force due to centripetal force is going to be equal to mass of Earth, radius of this one, and omega square, mr omega square. That's the way in which this Earth will be revolving around this one. Means this is the orbit of R, this is R the orbit. Whenever it revolves, mass of the Earth and R omega square will be the one which will be revolving. Okay, equate both this one. Gms me upon R square is going to be equal to me R omega square. This gets cancelled out. So what you need to find out? What is the thing is asked? How will you weigh the sun? Weight of the sun is question mark. So keep this one here itself. Mass of the sun is going to be equal to, this one goes here, R cube. What is this omega here? You can write it as 2 pi by T the whole square. And this one comes down divided by G. So how will you name it now? R cube 1.5 into 10 to the power of 8. The whole, it cannot be 8 because we wrote it as kilometers. Now we need to convert it to meters. So it's going to be equal to 1.5 into 10 to the power of 11 meters. So it is 11 the whole cube into 4 pi square divided by time. Now what is G? 6.67 into 10 to the power of minus 11 into time. What is the time here? 365 days. 365 into 24 into 60 into 60. You have to convert into seconds. Put all of them, you will get mass of the sun. And the mass of the sun is going to be equal to 2 into 10 to the power of 30 kilograms you will get. This is the one, after you finish all the calculation, you will get there, land up with this answer. Okay? Let us look at the next question now. Question number 4. A Saturn year is 29.5 times the Earth year. So here we are seeing there are comparison of two things. One is Earth, next one is the next planet, Saturn, and then the next is Neptune. That's all. So this is the last but one planet. Now, what is the time here to revolve around? The time of Earth to revolve around the Sun is 1 year. What is the time of the Saturn thing? It takes 29.5 times. So it is going to be 29.5 years it will take to revolve once. Almost close to 30 years it will take. So if it starts now, but from one point, and 2050 it will complete. This whole thing will complete in 2050. 30 years gone. Now it is asked how far is that from the Sun? From the Sun, if Earth is this one, how far? Now Earth radius is given here. Radius of Earth is going to be equal to 1.5 into 10 to the power of 8 kilometers. Now radius of Saturn from the Sun is question mark. Now that is the clarity that you have. But you know, radius of the orbit and time period. Look at this one. There is a variation here. There is a kind of a something combines these two together. We already studied this one in gravitation itself. We studied there is a radius of orbit and there is a time period of this one. So these two has a relationship. That relationship was given by Kepler. Kepler's law of planetary motion. According to Kepler's law, what is that? So it is going to be the square of the time period is directly proportional to cube of the radius between the planet and the Sun. So this is one part, and then square of the time period of Saturn also is directly proportional to TS cube. Can we divide both of them? So TE upon TS, the whole square, is going to be equal to RE upon RS, the whole cube. Only this one we know, and these two also we know. So how do we do that? You can have it as TE upon TS is going to be equal to RE upon RS whole to the power of 3 by 2. Because this will take under root and under root, then it will become 3 by 2. In this under root and 2 will get cancelled out. Here 3 by 2 will come. Now, what is TE? TS times of RE upon RS, the whole to 3 by 2. What is the time duration of the Sun? Now, what is asked? What is asked? How far away from the Sun? How far away from the Saturn is from the Sun? RS we need to find out. Alright. So let us, I think this one also you need to just little hold on this. So let me not put this one. Here itself we will see. This is 1 year. TE is 1 year. T is 1 year and TS is 29.5. 1 upon 29.5. And that is whole square. This is 1 upon 29.5. That is equal to RE is 1.5 into 10 to the power of 8 divided by RS. That's a whole cube. So now you can shift terms here and there. Alright, and then finally conclude what is the thing you will get. So if you take under root, here also you need to take under root. So it will become 1 upon 29.5. It's going to be equal to 1.5 into 10 to the power of 8 whole to the power of 3 by 2 divided by R also is whole to the power of 3 by 2. So you need to cross multiply this, you will get the answer. So please try to find out. So RS you need to find out here. Okay, I just dealt this one. Please try to find out. Okay, let's go to the next question. Yeah, let us go to question number 8. The distance of two planets from the Sun are there are two planets are there. The distance is given here, 10 to the power of 13 and 10 to the power of 12 meters respectively. Find the ratio of time period and the speeds of the two planets. Very simple, straight question. Again, Kepler's law we need to find out. Distance is given, time period is asked. So already we know t square is proportional to, the square of the time period is proportional to cube of the distance, r cube. T square is proportional to r cube. Please write down now. According to Kepler's law, the square of the time period, t square, is proportional to r cube. So in this one, t1 is given here. The distance is given here, r1. r1 is going to be equal to 10 to the power of 13. r2 is given here, 10 to the power of 12 meters. These two are given here. So, how do you find out? T1 upon T2, the whole square, is going to be equal to R1 upon R2, the whole cube. If I try to find out for both of them. So, it is 10 to the power of 13 upon 10 to the power of 12, the whole cube, is going to be equal to T1 by T2. If you want to find out only T1 by T2, what will happen here? So anyhow, this is getting cancelled. What you will get remaining? 10 only. 10 to the power of 3 by 2. Because the square is now taken, it will become 3 by 2. So it's going to be 1000 to the power of 1 by 2. This 3 is now gone down. So 1000, it will become 10 under root 3. 10 under root 10 is T1 by T2. Alright. Now we'll need to go to the second part of it. The second part of it is, what will be the speed of the two planets? This is the ratio of the timing. Now speed is given here. Alright. So we know velocity 1 is going to be equal to 2 pi r1 upon t1, and velocity is going to be equal to distance, circumference upon time, 2 pi r2 upon t2. v1 by v2 is going to be equal to r1 by r2 into t2 by t1. So we are asked to find out the velocities. Now what is r1? 10 to the power of 13. What is r2? 10 to the power of 12. What is T2 and T1? It is already given here. T2 and T1 is given here. So it is nothing but 1 upon 10 under root 10. Because T2 upon T1 means it is reverse. So what is the value here? This is already 10. Only 10 is there. Into 1 upon 10 under root 10. So this is get cancelled, this is also get cancelled. So what's the answer? V1 upon V2. So V1 by V2 is going to be equal to 1 by under root 10. So it's going to be equal to 1 upon under root 10. That is V1 by V2. Alright. So you can turn to page number 535. There is an example question. There is an exercise questions. Now, first question we need not do it. We are not going to do it. Second question. The mass and radius of a moon are, mass is given here, radius of the moon is given there. That is the diameter of the moon and the size of the moon. 1.75 into 10 to the power of 6 meters. Find the acceleration due to gravity at the moon. G value is given here. So they are asking you to find out the acceleration due to gravity at the surface of moon. How will you find out this? So we are always understood it is 1 by 6th of the value of Earth. That's what we know it. So 9.8 divided by 1 by 6, 1 divided by, into multiplication by 1 by 6 is you will get this answer. Let us see how to do it with G. So acceleration due to gravity on surface of moon, G is going to be equal to capital G m upon r square. This is gravity of moon. All things are given there. 6.67 into 10 to the power of minus 11. What is the mass? Mass of the moon is already given there. 7.34 into 10 to the power of 22. 7.34 into 10 to the power of 22. And then the distance is already given here. 1.75 into 10 to the power of 6. 1.75 into 10 to the power of 6. Now this is already whole square. That's it. Find out the value. You will be able to easily make it out. Okay. So try to bring out all the terms to the next side, and you will be able to have a clear understanding about how it goes. Okay. Now let us do it. 6.67 into 7.34 upon 1.75 into 1.75. What did I do? I have taken this one, I have taken this one, I have taken 1.75 into 1.75 whole square. Okay. Into all the powers. 10 to the power of minus 11, 10 to the power of 22, 10 to the power of this whole thing, it is 12. It goes up minus 12. So what you will get finally here? You will get here into 10 to the power of minus 1 you will get. Now this calculation if you put, you will get here as 16 you will get. So it's going to be equal to 1.6 meter per second square. That is G. Okay. So it's pretty simple. This is the value. Now based on this, I'm going to shift to another question here. Please take a look on it also. Turn to page number 506, the example questions, and try to look at the question number 6. Question number 6. The weight of a person on earth is 80 kilograms. So he is at earth, 80 kilograms. What will be the weight on the moon? Same question. What we did, the same question is here. Mass of the moon is given there. Radius of the moon is given there. That question also was there. Gravity is given there. What will be the mass of the person on the moon? So how do we do it? Same thing you do it. Exactly. So force is going to be equal to G into Gm upon r square we did because mass was, we thought it is there. Here already mass is given there as 80 kilograms. So G into M into r square, exactly the same the gravitational force. So substituting G value, mass of the moon and mass of the body which is on the surface of moon and the radius. If you do it 128 you will get. Okay. Now you need to back it up with the work done. Sorry, the weight upon mass is going to be equal to the value of acceleration due to gravity also will get. You will get 128 upon 80. Try to put it 1.6 you will get. So it is asked, what is the weight on the moon? It is weight on the moon is 1.6. Alright. So this one, after in the end of the time when we do it, so it's already asked one more thing. If a person can jump 2 meters in the on high on earth, how much he will be able to jump on the surface of moon? So that is a question there. Now look at the answers here given here. That's also pretty simple. So the person standing on the earth, the acceleration due to gravity is 9.8. So it is the first line. Therefore, for a person standing on the moon, the acceleration due to gravity is 1/6. It will be going to be 1/6. So the person also can jump 6 times higher than the top of the thing. Okay. So if he is jumping some distance in the surface of moon, alright, you will here on earth you will be able to jump only 1/6 of that. Or if you are able to jump 1 meter here, there you will jump 6 times. Hence the height of the jump on the moon will be 12 meters. Here there he is able to do only 2 meters. It is a high jump. In the high jump race, here only 2 meters he is able to jump. There he jumped so high, 12 meters. 12 meters is something 2-story, 3-story building. It is a huge, even our main new building, it will be 12 meters. So that much he can high jump when he is going on a high jump. So that's quite interesting. In moving on a plane, G does not affect. Hence the person will walk on the moon 100 meters. If he is walking, it takes 1 minute. So he will also walk the same way. He will be able to walk same way, but definitely when he jumps, he is going to jump very much higher in moon. Alright. Okay children, with these questions I finish. Hope you have noted down. So note down clearly. If you are not understood, please take an effort to do it again. Try to just go through these questions once again. It will be quite helpful for you when you go with yourself and try to have a look on it. Okay. Alright. Next class I will be doing with acceleration due to gravity in various cases that we will do. Okay. Thank you.